Following on from the previous video, we were trying to find the intersection of two planes. So the intersection of two planes will give us this line. And the trick into finding out the equation for this line is to realize that the two normal vectors, n2 and then n1, the trick into finding out the equation for this line is to realize that these two vectors, they lie flat on a surface. So you can actually lay the two vectors onto a flat surface. Now if these two vectors lie flat on a surface, then you can use a cross product, and then that will then give you the vector that's orthogonal to the two vectors. Well, the trick into finding out the equation for this line is to realize that these two vectors lie flat on a surface. It might take a while for you to be able to visualize that, but if you can visualize that, if you can realize that these two lie flat on a surface, so you can place them on a table, then you should be able to accept that if you take the cross product of the two, then it will then give you this vector. Well, this vector will be used to describe this line. All that we need now is to find find one particular point on this line. Well, let me give you an example. So, looking at an example, let's say we've got one plane given by this. Let's just say this plane here is this red one here, and then this one here is this one here. So the first part is to find the normal vector to the two planes. So the normal vector here can be extracted from here. So this will be your normal vector. So that's this normal vector n1 here. That's this normal vector here, and then the normal vector for the second plane will be given by 2, 1, and -2. So this is your n2 here. This is your n1 here. Well, if you can realize that, if you can accept that these two vectors lie flat on a surface, meaning you can lay them on a flat surface on a table, then blindly compute the cross product of the two. That will then give you this vector here. Well, this vector here will lie will be in the direction of our line. So compute the cross product of these two vectors. So compute the two cross product. So the cross product, your eyes should zoom into this. Discard this times this, take away this times this. That will then give you this. And then your eyes should zoom into this. Discard. Look at this. This times this, take away this times this, blah blah blah. And then don't forget you've got a minus, blah blah blah. It will then take you to here. Okay, so this thing here will represent this vector here. So now that we've got this vector, all that we need is one particular point on this line. It can be here, it can be here, it can be here, it can be anywhere. We just need one particular point on this line. So hang on. So this thing here describes this here describes one plane. This here describes another plane. Well, any point on this line must satisfy these two equations. So we are looking for one particular point on this line. Well, anything that lies on this line must satisfy this and this. So we just need to find one particular point on that line. So finding one particular point on this line, let z be 0. So hang on. So you've got your x here, your y here, your x, and then your z here, so z here. Let z be 0. So you're discarding the vertical. So you're just looking at the flat surface. You're just looking at the floor, if you like. You're not considering the height. So we are just trying to find one particular point on this line. The trick is to let z be 0. So now we are just considering something along the line of along the plane of x, along the xy plane. We are letting z to be 0. So we are trying to find x, y, and z in such a way that these two will be satisfied. So let's just look at a case where z equals 0. So looking at a case where z equals 0, z equals 0 would be us just looking at the xy plane. So it's like a flat surface. It's like the floor. So we are ignoring the height. You could. I'll explain some more another time. So let z be 0. So when z equals 0, when z equals 0, then this thing here will then become this. So now solve this simultaneous equations times everything here by 6. That will then give you this, and then get this plus this, blah blah blah. X, y, and z equals this. Well, once you've got your x here, then go back to here. Once you've got your x here, go back to here, put it into here, and then once you've got your x here, go back to here, put it into here. This will be 6, so y must be negative 1. Z equals 0. So hang on, let me think. So what we've got here is we know one particular point on that line. This is one particular point. So you see, at this particular point here, at this particular point here, we know that these two will be satisfied. So that particular point could lie anywhere along here. Let's just say it lies here. Okay, so we've got one point now. We've got one point here. Let's just say that this point here lies right here. It could lie anywhere, but we know that it satisfies the two equations of the plane, or of the two planes. So we know one particular point. So now it's just we know one particular point, and we know the vector, so we can put it into an equation. So this is our equation for this line here. So now looking at the x component, it will be x plus 14t. Now looking at the y component, it will be negative 1 and then 2t. Looking at the z component, it will be 0 plus 15t. So this here will then describe the equation of this line. And earlier back here, I said let z be 0. Earlier we were trying to find one particular point on this line, and I said let z be 0. Meaning, hang on, you've got your x, y, and z. By letting z to be 0, we are just looking at the flat surface here along the xy plane. You could let z equals 1. So then 1 is here. Then you are looking at this plane here, slightly higher up. Or, well, basically you're just trying to find one particular point on this line. You're just trying to find one particular point where these two will be satisfied. You could actually say let y be 0. So if you look at your x, y, and z here, by letting y equal 0, this you're discarding the y direction, in which case you are just looking at this plane here. You could say let x be 0. If you let x be 0, then you're discarding the x direction, and then you're just looking at the vertical plane, and so on. Well, I hope you can follow that. Well, the equation for the equation for this line here is given by this. Okay.